All right, guys. Sorry I couldn't be there today, but we're going to talk about inverses of functions today. We're going to attempt to work through the target 1A and the target 1B notes because they're really very similar, and there is actually a lot of content that you actually are familiar with. So we should be able to work through those pretty quickly. So let's just start by talking about what an inverse is. These are some real life inverses: tying your shoes, untying, writing a sentence, erasing or deleting it, closing a door or opening a door, right? And here's the idea is that inverses will undo each other. That if you start with the door shut and you open and then close it, you go back to where you started. And if you start with tied shoes and then you untie them and retie them, you've now performed both inverses and you're back to where you started. We've done this in math since you were in middle school, right? Solving a two-step single variable linear equation here. We use the additive inverse to cancel the -4, and we use the multiplicative inverse to cancel the coefficient of 3. Remember, dividing by 3, which is what we're doing here, is actually the same as multiplying by 1/3, the multiplicative inverse of 3. All right, so inverses is something we're familiar with. So let's now apply this concept of inverses to our relations and our functions. Before we get into that, let's now make sure we remember what a relation and a function here is. This was algebra here. You covered this. It is on the wall in the back of the room. So if you need to take a look, just glance back at the wall. Right? The relation is a set of ordered pairs. Domain and range values generally are called the x-coordinates from our horizontal axis. Range values are the y-coordinates from the vertical axis. Now, a function is a specialized relation. I use the analogy that you have the regular members of the Navy. Anyone who's on a ship, anyone who enlists is in the Navy, but then you have the specially trained Navy officers, the Navy personnel. Those are the Navy SEALs, right? So a function is a Navy SEAL. If the relation is just everyone in the Navy, the functions are the specially trained ones, and those are trained so that they will never have an x-coordinate paired with more than one y-coordinate. If we look below here, this is an example of a relation that is not a function because you can see 7, a domain value, is paired with 2 range values, 2 y-coordinates, -2 and 11. All right, so now we reviewed relation and function. Let's talk about inverses. Now, finding the inverse of a relation is really easy. All you have to do is switch the domain and range. You literally just take each ordered pair in the relation and flip the domain and range. So in this example here in the purple, you have a relation of 3 ordered pairs, and then we get the inverse in blue by flipping. Now, an inverse function is an inverse relation, which is also a function. Now, here's the catch. Just because you start with something that is a function does not mean it will end up being a function. So it's a very special situation when you have a relation which is a function whose inverse is also a function. That's like the most highly trained Navy SEAL, right? If you've seen the movie American Sniper, that's like in a one-to-one function is what we call that, where it's a function, and when you take the inverse, it still is also a function. All right. Now, what we are essentially doing, as we said here, since a function takes an input value and turns it into an output value, when we reverse that process, we're just flipping it around here. All right, let's take a look at a couple of these examples here. So the first function we have is called f. So we know it's a function. The question is, what's its inverse? Is its inverse a function? And then does that make f a one-to-one function? Well, let's take a look here. Now, our notation for this is just going to be an exponent of -1. All that really means is it's just telling you that it's the inverse of the original function. It does not mean you should actually use -1 as an exponent in your calculator. Please don't do that. But finding the inverse is really just as easy as we said. We take each ordered pair and we flip the x and y. So instead of -3, -5, we have -5, -3. -1, -1, you can't really tell if it's flipped because the x and y coordinates are the same. But the rest of them, it is pretty obvious that this is an inverse. And I just realized a very easy mistake to make, guys. Don't make that mistake and write down the same exact ordered pair there. Now, we have an inverse. So the second question we have to answer, is the inverse a function? Well, as we look at these x coordinates, notice we do not see any ordered pairs that have the same x coordinate paired up with a different y coordinate. So the inverse is a function. So now this takes us back to our definition of a one-to-one function. So the original relation is a function. The inverse is a function. So that makes this original function a very specially highly trained Navy SEAL sniper officer, Chuck Norris Delta Force type combat soldier, and they are a one-to-one function. Looking at it as a table is even probably easier. Now, one thing to notice here, guys, on this table is I had, for some reason, the notation, the -1 was in the wrong place. The -1 should go between the F and the X, the G and the X, not after the X. Again, that's just how it's notated, but it's just as simple. I take all of the domain values from the original function, and those become the range values in the inverse, and all of the range values in the original function become the domain in the inverse. So the real question is the inverse a function here? Well, let's take a look. Do we see any x coordinates paired with more than one y coordinate? The answer is no. So the inverse is a function. So what we know, the original function is also very, very highly trained, specialized one-to-one function. Take a look at a graph. Now, you're going to have to add a few ordered pairs in. I realize I didn't put these 4 specific points right here, so go ahead and add those in on your notes. But the easiest way to deal with this as a graph is to find several ordered pairs that you are sure of and graph those, and then use those points to draw the full function, the full curve. So g of x is clearly a quadratic. It's a parabola opening down. So let's look. This ordered pair right here is -6, -2. So what I have to do then is flip that to go to -2, -6. So that point right there and this point right here are inverses of each other. All right, and so now what I'm going to do is just go ahead and take the inverse of each of these. So -4, -4, well, that one's easy because it stays the same. We have -3, -7. So I flip that, so I go -7, -3, right? So they have those two. Let me change colors again for these over here, right? We have -8, -4, so that's going to flip to -4, -8. And this one is -9, -7. So that will flip to -7, -9. And you can see now the green, blue, and red points up here, I graphed them as their inverses down here. And then all I have to do is you connect them so that the curve makes sense with the points I have. So this is g of x up here as a quadratic. This is the inverse of g of x down here. Now, what we can see here is that this is not going to be a function. This does not pass the vertical line test. There are many places you could choose to do this. I'm just going to graph a vertical line right here through -4. What we can see is that we have 2 points, 2 ordered pairs, -4, -4, and -4, -8, that have the same x coordinate but different y coordinate. This means this is not a function. So this is how we find the inverse of a function from its graph and then determine if it's an inverse, right? So we see this was not an inverse because the 2 ordered pairs with the same x coordinate and different y coordinates. So this is not a function. Sorry, it is an inverse. It's not a function, which means the original is just a function. Just a function, not a one-to-one function. Not one-to-one. All right, so I left you several examples here to try on your own. B, D, and then B, and then C and D over here. I will add the correct answers into real-time board so you can check those out. Let's now talk about equations. We've looked at finding inverses of a table, of a list of ordered pairs, and of a graph, right? But what happens if you're given the function as an equation here? Well, this first part was a review. If we had done these in 2 days, we would have done this first part as a review. I filled that in for you so you can take a look at it for another example. But the biggest idea here, guys, is that we're going to apply the same concept. If the inverse is found by switching the domain and the range, then what we are going to do is switch the domain and range. But in an equation, we have variables which represent every domain and range value, and normally those are the x and the y variable, or we all know what fx says, y, right? And so essentially, if we're going to apply the same concept, what we're going to have to do is we are just going to have to switch the domain and range, the x coordinate, the x variable, and the y variable. But whenever we write a function, whether it's an inverse of a function or the original function, we always write it with the range or output variable, y or f of x, as alone on one side of the equation. So once we flip x and y, the key is then we are going to have to solve for y, which means to isolate the variable. So pretty straightforward here. So let's do an example together. First of all, I think it's easier to work with our equation with the variable y rather than f of x. You do not have to replace f of x with y to change the variable, but I think just writing f of x over and over again is going to be more tedious than it's worth. So switch f of x and y, and then what we're literally going to do is we're literally just going to flip-flop we're going to crisscross here where x and y are. So what we'll end up with is x equals the square root of y, right? And that's the inverse, right? And if it was acceptable to leave it that way, we would be fine. Here's the catch though. To be written as an inverse of f of x, since f of x or y was alone to start, we have to end with f of x or y alone. So we need to do whatever we need to do in the equation so that y is alone, not x, which is where we're at right now. So the question becomes then, what do we do to get y alone? Well, this is a root of 2, right? A square root, a root of 2. And if you think back to algebra, we cancel a square root with an exponent of the same power of the same value. So I use a power of 2 to cancel a root of 2, but whatever I do to one side of the equation, I have to do to the other. So what I end up with here is x squared equal to y. Now, that is the inverse, but since it's written in function notation at the start, we want it written in function notation at the end, because in function notation, we can show clearly that it's the inverse of f of x, where if we just use y, it's pretty much impossible to denote that. So this would be the expected final answer for the inverse of f of x. All right, let's do one more together, and then I'll turn you loose really to practice the rest of the problems. Oops, we'll do 4 together as well. So here we go. We've got h of x. I replace y, right? So I just flipped my notation there from function notation to regular notation, and then we're going to replace x with y and y with x, right? So I'll end up with x equals y minus 4 over 3. As Joey did before, we now have to isolate the range variable y. So I've got to get it alone. First thing I've got to undo is this division by 3. So what I'm going to do, just like we did in algebra, I'm going to bust out the multiplication property of the equality trident missile system, and that will destroy the denominator of 3 over here and multiply the x by 3 on the left. Then I will cancel the constant of -4 by adding 4. Now these are not like terms. Please do not write 7x. Just don't do it. Just please don't do it. Right? And now that we're done, we now have to go back to function notation. Since we started with h of x and we have the inverse, we now need to write this as the inverse of h of x. All right? So hopefully that gives you a feel for what we're doing here. It's really the same thing we did up here, where we switched the domain and range, the x and the y, just now we're doing it as variables rather than individual coordinates, or ordered pairs points on a graph here. So what we can also use this method of finding an inverse of a function from its equation for is proving whether different functions are inverses of each other. And it's really pretty simple. You pick one of them, you find the inverse, and if its inverse is the same as the other function, then they're inverses. So let's start with f of x here. I'm going to choose f of x. You really could choose either, but it comes first, so why not choose f of x? I'm going to change f of x to y just to make my life easier. I'm going to flip x and y just like we did. If I'm going through these steps too quickly, please either send me a message in Schoology, or you could ask me a question through ClassKick, or just wait until I'm back at class and we could talk about this. But I'm going to subtract 2 from both sides here, and then I'm going to divide by 6 here. Now you might be saying to yourself, well, that does not look like g of x at all. And we know we're going to change this to f of -1 of x here. And there we go. So now we've done exactly what we did on the previous page there. We found the inverse of f of x. You might be saying, well, that doesn't look anything like g of x. Well, but here's the catch. This is written as one fraction with 2 terms in the numerator, and this is written as 2 separate terms. If we were to separate these 2 terms and write this as x over 6 minus 2 over 6, well, really what we have here is our ninja coefficient of 1. So you can see that that really is 1/6x, and 2 over 6 will actually simplify, oops, got ahead of myself there, will actually simplify to 1/3. So you can see that the inverse of f of x is actually the identical equation that we have for g of x. So since f inverse of x is equal to g of x, they're the same equation. That means f of x, the original function, and g of x are inverses. All right, and if they were not the same, if what you ended up with down here with f, the inverse of f of x, was not the same as g of x, then f of x and g of x would not be inverses. Pretty straightforward. So a couple more examples here in these notes for you to work on. Again, I will put the answers in real-time board. You have a homework, you have worksheets in the worksheet packets that I gave you to be practicing. The answer keys are on Schoology. So you have the rest of the time to work on whatever you need to work on, whether that be homework, whether that be problem in the notes, to get yourselves ready for tomorrow. We'll have a chance to ask questions about the notes and the homework, and we will be doing most likely a formative assessment on this skill about our inverses. Hope you have a great day, and I will see you soon.